Hi everyone, my name is Daniel Cumming, and I'm here to give a guest lecture about Rust and ownership for Ackee. I can be found at this Twitter address. I don't use it very actively, but if you want to find me, I'm there. And some more information about me. I have worked with runtime verification for the last 3 years. And at runtime verification, I've worked on mere semantics, which is building a formal methods tool called K and called Compass when applied to the Solana ecosystem. And I've also done some teaching for Rust. I have done and continue to do the Intro to Rust course for Rare Skills for the last year. And at Rektoff, I wrote the Module 1 Rust Theory and Fundamentals course for both cohorts that have run in 2025. So Ackee and I had a discussion, and they said that they would like me to talk a bit more about Rust. And I gave them some options, and we decided that the best thing to talk about would be a bit more depth into ownership and why we have it, why we want that to be part of the language that we use in Rust. So, in particular, what I'm going to talk about is wait, if I have some notes, I should get them ready. In particular, what I'm going to talk about is ownership, but I don't want to jump into ownership straight away. What I want to talk about is the motivation for it. I think the best way to approach learning something is to understand why do we want it. So number one, we're going to talk about motivation, and the reason that we want this is memory safety. So after that, I'll obviously talk about ownership generally, but with ownership comes some rules. So I'll talk about this particular rule called exclusive ownership. I guess that's talking about ownership generally, but after that, with the restrictions that come with the exclusive ownership, we want to have the ability to borrow, to have references to otherwise owned data, and that comes with another rule called aliasing XOR, as in exclusive OR, aliasing XOR mutability. And so hopefully within a reasonable amount of time, I'll be able to cover in some detail this information. So let's begin with the motivation, as I said. Maybe another thing that I'll say is all of this information that I am going to communicate with you is from my understanding as someone who has spent some time reading inside the Rust compiler, reading blog posts, reading articles, and writing programs and investigating how this works, reading mere. But certainly, my understanding is not perfect. There could be mistakes, and there might be better ways to understand or explain this. So don't just stop at something that I'm explaining. You should investigate for yourself and also seek other sources. But back to the motivation. Well, really, it's just memory errors suck. They end up being a source of vulnerabilities. And if we can eliminate them from programs, then our programs are indeed a lot safer, which is, what Rust tries to do. It has memory safety. So Rust gives us a guarantee. It guarantees at compile time. So not at the point. So what I mean at compile time is this is not our program running. This is as we're compiling our source code down into a binary that binary can be executed. But at compile time, we want to know that we have memory safety. So Rust guarantees at compile time that the binary is memory safe. If it's not going to be memory safe, if it has a memory error, so that's memory safety being the absence of memory errors. So if it's not going to be able to do that, we won't get a binary. The compiler is going to complain. It's going to tell us where did we screw up, and it's going to show us in relationship with ownership and moves and lifetimes, this sort of thing. But let's have a think, because I think so. Let's have a think of something that's a bit before memory safety. Let's have a think about memory. So I think this is something that maybe in a blockchain context can be overlooked. There's a lot of people coming who maybe haven't done a ton of programming, and so I think it can be useful to sort of draw out or map out some ideas of what's going on with memory. So maybe before I map them out, let's talk about some states. What are some states that memory could be in? Well, there's unallocated. And so this is a state where we haven't, our program, our operating system hasn't provided to our process, our program that's running, it hasn't reserved the memory for us. And so what state is that in? We know that our computer really only understands zeros and ones. So is this in a state of zeros or is this in a state of ones? And the answer is we don't really know. If we were to try and perform a read or write of unallocated memory at some address, let's just make up an address, 123 is my fake address. So this slot of memory at 123 that I like to give a little picture like this, we don't know what's there. We don't have any guarantees of what could be there. It could be that we read something that looks like random ones or zeros, or maybe our program will error. We don't really know. So what we consider is it's not permissible. If we don't know what's going to be there, it's not permissible for our program to read or write from this address. If it's unallocated, we're not allowed to read or write. But this is the state that memory starts in, I guess I should say. Memory starts in this state, starting being prior to allocation. And I guess maybe we can think, after we deallocate, I guess, we can think it ends here after deallocation. So we sometimes refer to that as freeing, or maybe we can think of that as dropping, but after we've finished using the memory, then we're not allowed to perform a read or write for it. That's it. It's a banned location to read or write from. So another state that our memory could be in is uninitialized. But this is allocated, so it's also allocated. So it's uninitialized, but it's also allocated. So what does that look like? Well, if we grab this, it's similar. So now, if unallocated, we're not allowed to perform a read or write, and we don't know what's there. But if it is allocated but it's not initialized, then it's not permissible for our program to read from there because we don't know what's there, but it is permissible for us to write to that location. So we can go and we can perform a write to 123, and that would be initializing our memory. And so memory goes to this state after allocating prior to writing. And then a third state that is good to think about is initialize. And this is probably the one that we're most familiar with. And this is where we might have some value. Let's say 255. we have 255, and that might come from a situation where we have like let x as a U8 be equal to 255. And so if we think that x has some address, let's just say for the sake of this that the addresses are OX123, which is, just a fake address just for the sake of argument, then we can think that in some way there's a slot in memory which is now holding the value of 255. Its address is 123, but that's corresponding to x. So it's our x is equal to that. And this box is at address, this x is at address 123. So it is permissible for our program to read and write. We can perform another write. We might modify this location if we have mutability permissions and update it to 42. And we can read the 255 from this location. Memory goes to this state after our first write. It's after our first write, because prior to that, it's uninitialized. So maybe a better way to represent this would be a table. So what are our states? There's unalloc, there's uninit, and there's init. So making a table. And we'll go read. So unallocated is not allowed to read. Uninit is not allowed to read. And init is allowed to read, we'll say yes. But what if we want to write? That's not allowed if we're unallocated. That's allowed if we're uninitialized. So we've allocated, we can perform our first initialization. And assuming we have mutability permissions, we would be allowed to write there. So I guess something that we get from the Rust compiler is it wants to enforce this. So Rust memory safety enforces this. It doesn't allow us to read or write from places where we don't know that there's well-formed data at those locations. But it's actually, there's even more than that. It goes further. So Rust goes further than that. You must have a valid origin to get to the init memory to read or write. So what does that mean? Okay, that might not be clear, but if we think of 2 blocks of memory, this one, whoops, maybe I want that. So we have 2 blocks of memory. Here's our first one, and here's our second one. Maybe they can be contiguous like this. So let's say that y is on the bottom. It's equal to 42. X is on top. So x is address. Let's make it something easier. 100. And the next address, or maybe I should go, this is 180. And this is 100 address. So 8 bytes. Did I get that right? Yeah, I think so. 8 bytes up. Assuming that the addresses go up as you go up the page. So this would be coming from something like let x be 255, and this would be from something like let y be equal to 42. This is pseudocode. Like it's, I'm trying to represent things visually. Let's attach this to a program so I can illustrate my point better. So, what would this look like? It would be a main function that has inside it, let x be equal to a U8. That is 255. It's right there. No, wait. Sorry, 42. I got them the wrong way around. And x was 255. So we have something like this occurring. Now, what I mean when I say you must have a valid origin to get to init memory is we can kind of think that X is responsible for 255. This X isn't really stored in the memory location. Like, we don't really see inside this box. This is zeros and ones, and the zeros and ones are going to be of the form that show us 255. But we know that at this address, we came to there because we assigned to the variable X 255. And we know that in this slot of memory, which is at the address OX 100, we know that we assigned to Y 42, and that's why there is 42 in this location. So Russ says, well, if you want to do a read and write of Y to get to this 42, you have to go through Y. You can't do something sneaky. So normally we would have, something that you would be familiar with is if you want to read from Y, you do something like this. You just go and read from it. What you wouldn't do is if you wanted to read from, let's say you wanted to read from X, you wouldn't go to Y and you wouldn't create a reference to it. The reference would, in this pseudocode world, the reference gets you back to, or the reference gives you this address. You can't do something like give me the reference of Y, and then I want to add to that 8 bytes. This is pseudocode. 8 bytes, and then perform a read from there. And by doing that, we go up and this reads 255. Say this prints X / or X, and that is 255. Rust doesn't want to give us the ability to do something like that. What it says is it goes, hang on, wait, if you want to go and you want to read the 255, which is at this slot here, you can't go to Y and perform some, trick and then start mucking around with the data that's behind X. If you want to get to X, you got to go through X. And this is where the idea of ownership comes in. So this sort of strictness is to stop us getting memory into a bad state or having unsynchronized reads and writes or invalid accesses. The purpose of it is to keep memory safe, and so I'll show you an example of that soon, but let's talk about what is ownership. So first, this idea of if you want to get to the values that are behind the variables, that's ownership. So as I just said that, ownership is a relationship between variables and data. So data being values stored in memory. What else should I say here? So that data that's in memory, it needs to be owned by one variable. So this is that exclusive ownership principle. So data in memory So that whatever the relationship that I'm about to describe, that occurs between one variable and the values behind it. So one variable and the values. So data in memory is owned by one variable only, thus exclusive ownership. The variable that owns the data, like what do you get if you own the data? What does it mean to own it? So the variable that owns the data dictates, or maybe not, yeah, dictates the read and write permissions. So you control who's like the read and write of this data. So if you want to read this or if you want to write to that slot to update it, in safe rust, so unsafe rust is different rules, but in safe rust, you got to go through the variable. And it also, with ownership, you also control when the data is dropped from memory. Or dropped, maybe I'll say freed, maybe I'll say destroyed. Like as in when is it getting kicked out of memory? Or when is it invalid to access that location of memory? Yeah, maybe I'll write that out. So by drop, I mean there is no variable that can legally access the data. And so it is effectively removed from memory. As I said before, unless you use the unsafe keyword, you can perform these tricks in those occasions. Okay, so that's my description of ownership. There's my theory to start off is, what is our motivation with memory safety? Well, we can get our programs into really bad states if we start reading uninitialized memory. Maybe people have some way of forcing values to be in certain positions, and then they have ways of having our program read these invalid blocks. So if they have the ability to write or read from these places, we can get into a whole world of hurt. So we have this idea that we want to be able to like have particular permissions on zones of memory. But further than that, we want to know that if you are reading from initialized memory, that you're reading through a variable that has ownership of it, that is responsible for it, and this variable can choose the read and write permissions of the values that it owns, and it can also choose when it wants to get rid of them out of memory. That's the recap there. So let's go in and have a talk about it. Or not have a talk about it, let's go in and see some code for it. So if we have something like let v be a vec storing 1 and 2. Oops. So then here, v owns the vector. So what does that mean exactly? Like what is the vector at this point? I think we can go in to the standard library and have a look at what is this vector? Well, the vector is a struct. So there's some information here which is going to be stored on the stack, but also by way of the fact that this is making a call to the allocator, this is going to store some memory on the heap. So inside the raw vec here, if we go in deeper, we'll see that there's a pointer, and this allocator is going to allocate some memory on the heap up to a capacity for us to store the values that we think of as the contiguous block in memory. So let's take that. That's going to be useful. But in that documentation, there's a nicer description. But whoops, ignore. Maybe I should make it documentation like this, and it will all go better. Nope, that was where I copied that. There we go. So this stuff not so useful, but we can think of the vector as having this struct component, which is going to store a pointer, a length, capacity on the stack, but then it's going to store on the heap our values in memory, but it's going to allocate more than what we need as we start adding to it. So let's see what I mean by that. I mentioned that there was some nice visuals to go with it, and so this visual here shows what's going on. So let's bring exactly this back. Whoops, wrong way. Nice. So this struct here is stored on the stack, and here's our representation of it here. So we aren't storing these characters. We're storing 1 and 2, like so. And at this point, we don't have this uninitialized here. When we start, we have something that more looks like this. Oops. So this is the initial state of our vec. So this is the data that our variable v owns. It owns the pointer to the heap, which is stored on the stack. It owns the value of 2 corresponding to the length, and another value of 2 corresponding to the capacity. And if you follow that pointer, it also owns the heap allocation, which is storing our payload, our 1 and 2. And so I'm going to put that back, because what we can think of is read and write permission. So if we want to read from this vector, we have to go through v. So when we print line of v, whoops. Let's get rid of this hello world. We don't need that. We have to go through v to, oops, did I not save? We have to go through v to read our values. This is reading the values. Much the same, if we make this mutable, then we do something like v.push 1. This is our legal way of going and modifying this data. So, whoops. So if we print it out again after that point, what happens when we do this push is we want to extend out. We want to write in some area that doesn't exist yet. So I guess I shouldn't have put that back. I just didn't want to have to rewrite it again. But this is the state of our vector beforehand, and that's what we print, that's what we see. And then we want to push, and we see, okay, we're going to need to write over the ender here. So let's double this capacity. So we double the capacity. It's uninit at this stage. We've allocated more space. So going back to here, we weren't able to just go and write into this space here. We weren't able to just go and write. We had to go allocate some more space, which is what is the work being done by this allocator here. And then once we've allocated that space, we will update our bookkeeping. So this is changed to 4 now. Oops, get the cursor out of the way. This is changed to 4. And now we're allowed to go and write from this position. If we wanted to read from that, it would not be allowed. But we can go and write to this position now. What did I do? I pushed 1. Let's push 3 instead. That sounds like a better idea. So here we have, I'll make it nice and neat, otherwise I'll not sleep tonight. So now we have our elements that are the payload of our vector stored on the heap memory, but we need to update our length. So you can think of as this is the boundary of how long we're allowed to read from this position. So this pointer points to the first element, and then the length says you can read for this many elements along, and you can write for this many elements along. And then if you want to go and write in the next position again, well, that's on allocated memory. You have to perform an allocation first to go and get some more memory. Okay, so if we do something like this and we say let v2 be equal to v, if you're familiar with Rust, you'll know that this performs a move. So with ownership, ownership is exclusive. So you can think of this is essentially trying to copy the data. You're saying, in my variable v2, I want the data or the values that are inside v. We'll copy them into v2 in some way. So if ownership is a relationship between the value and the variable, then another variable wanting to come and have them, that performs a move of the ownership. We want ownership to be exclusive. You have exclusive read-write access. If you want to do reads-writes, you have to go through this variable. And so now that v2 wants that data, we get a move. So the data is moved to v2. V is now invalid. It's invalid to access the variables there. So what does that mean? Well, you've probably all gotten to the point where you've seen something like this, where you go, okay, let me print my vector now with v, and the compiler tells you you're not allowed to do that. So if I show the error message, we are trying to access a moved value. So with our diagram, what can we think of that looking like? Well, if this is v, so v is here, maybe I'll make a bit more room. V is here like this. Let's shift this over. Whoops, maybe not that far. That's nice. So this is still pointing to 1. When we do this move of v2 equals v, something similar to this occurs. We create a v2, which is at a different address, and that... this is what I want to do. Maybe this arrow. And then I can do this. Oops. This is what I want the diagram to look like. Okay, cool. So what we have is V is pointing to this. We bring the data and the values over to this V2, and it has the same information. So this move here meant that in a different location of memory, so something to note is that when this move occurs, I'll note that think of, how should I say this? I guess V2, the reference to it, like these are not the same. Maybe I should just say that like this. Not this isn't real notation, but like v2.address in memory does not equal v.address. Like these are occupying different hex numbers like this. But at those different hex numbers, the values are the same. So what the move does is it says, you're not allowed to go here and access these ones anymore. If you want to access these values, now you have to go through V2. And so that's why we get this error here that stops our program from working, because if this is now like poison, we're not allowed to use it anymore. We're banned from using it, which I represent by putting exclamation marks around it. It's moved. Well, then, if we try to perform a read from it like this, that's not allowed. But what if that wasn't true? Why do we care about something like that? Well, let's have a think of what if this program, first of all, before anything like that, before we worry about this stuff down here, what if this was performing a drop of V? And then we were trying to do a read like this. A drop of V says disposes of a value. Does it tell me about heap? Maybe it doesn't, but what we can think of is when we say this drop V here, it's doing this. It's invalidating V. We're no longer allowed to go to V. And what it's going to do is it's going to see that we have a pointer on the heap, to the heap, and it's going to go and it's going to deallocate this memory. So when we drop it, we go and we free up that memory. We allow it to go back into the system to be reallocated again. So it changes from, I guess, all of these change to unalloc, maybe. Oops, what did I have it up before? I had unalloc. So all of those positions here, even these, they change to unalloc, which, it might be tempting to think that what's there is going to be the same values as before, but I encourage you as an exercise to do something like drop this location. And, I'll write this exercise. Store the value of V, store the address of V, and use unsafe rust to, I should say, of V0. Go look at this position on the heap and use unsafe rust to read after V is dropped. Because you might think, well, the same information is just going to be there, but that isn't necessarily true. And on, I think, any typical operating system, that won't be the case. There's other uses for that memory, and you're not meant to be going and reading from it anyway, so it shouldn't be a problem that memory gets used for other purposes after you've dropped it. But if that's what happens when we drop V, well, let's imagine that we do a similar thing. So now we're going to go to imagination land, and we're going to imagine that, so imagine V is still owning the values. V2 and V share ownership of the values. So imagine that were true. Well, we could then enter a situation like this. After we've performed this move of V to V2 and we have the dual ownership situation where this is no longer an illegal variable to access, then we could get into a situation like this where I go, okay, so let's drop V2. So this is going to go along here, and this is going to change. I mean, whether or not it's going to change everything, let's just imagine this is true. So we're going to change it to unalloc. I'll just change it to X. 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 And we follow through that pointer, and we go and we change this to X. These are all unallocated. We're not allowed to go there. And, whoops. And this has happened. We're not allowed to use V2. But, no problem, because in our world of shared ownership, not exclusive ownership, we still have V. So this drop of V2, it has, where does it say? Disposed of a value, which has gone through and deallocated our memory up here. But why don't we do our print line now? And so, of course, the compiler is not imagining with us, so it still has a problem. But let's think, what would this print if this were allowed to do this? It would go to this pointer, follow it through to this unallocated memory, and it would print these three positions. And this is now the situation where we're reading unallocated memory. So we don't know what's going to be there. All bets are off, essentially. And this is the kind of thing that the Rust ownership system is trying to prevent. So exclusive ownership stops us from getting into situations like that where we can go and free some memory and do something like that. It does a lot more than that, but I thought that might be a nice example to show that if we didn't have this system of exclusive ownership, just something simple like a few lines of code like this, and we can see with the diagrams that this wouldn't make any sense. And so, of course, Rust bans us from doing something like that. Okay, on to the next part. Aliasing XOR mutability. So maybe first, let's have a think for why we might want something like that. For this next section, I'm going to just get rid of this. I think let's start a new section. Let's just call this borrowing. I'm going to print other stuff, and so I just want a new context to work from. So just call a different function. Okay, so maybe let's start with some motivation. I guess I'll just do the same thing. We'll work with a vector 1 and 2. Let's think. Something that we generally want in programming languages is the ability to do computation in another context. But if we have ownership where we're really restricting the read and write permissions of values in memory, then how does this work for moving stuff to another context? It is possible to work within the ownership system. Like we could have functions. I guess we could have like do reads. I'd make up some computation. So do reads with v, and we could make or do reads. Do writes. We're going to do writes. I'll need to make this mutable. But we could figure out a way to do this. We could have a function do reads, and this could take v, and we can make it a vec of I32. So it's going to take ownership of v at this point. Maybe I'll change it to arg, so the naming isn't so bad. And this could just return the vec back after it takes ownership, and so providing it back to the other context. So let's do some reads in here. We can print line for our v. No, arg is what it has to be. So, yep. And then, I guess I'll have to provide arg, and then I can do a similar thing. I can do writes. And I should do some writes. So arg dot push 3, I guess, because 1 and 2 up above. And I'll need to make the argument mutable. That's what it was just complaining about. So it's unhappy here because of use of a move value, and that makes sense. So v here is being provided as the argument to do read. So ownership is moved inside this scope so that we can do our reading computation, and this argument is then provided back out as a return variable, but it is never captured, and so I need to capture the return values back into v, and so now ownership starts here, it moves into do reads, it then comes down to the end through arg, it goes back into v, it then goes into do writes, then comes back into v. And so I could print this out. So in do read, and maybe I'll do it after here just to show. Whoops. Arg. Of course, it's v. Nice. So now, and that's what we expect. So we have a way of doing this computation using ownership, through this return system, but no one wants to do this. This is lame. It's memory inefficient to be doing this. Instead, what we'd rather is to provide that address. We want to be able to provide the address of v into here, and then read from that address or modify that address, because as we remember, this is a struct that has a whole bunch of values on top of it. So we want a better system than this, and there is a better system. We can use borrows, but what does that mean? Because ownership is about having total control over the read and write permissions. So when you're going to allow someone a reference, how do the read and write permissions work, and do they affect the owning context? And as we'll find out, they do. So I'll write a bit of I don't know, theory. I like writing things out. So aliasing XL mutability is the context that we have here. So I mentioned that are there rules about the reads and writes? There are. In particular, this is the shorthand. And so what does that mean? Well, what it means is you can create multiple read-only references / borrows, or, well, XOR exclusive OR, so you can't do both. You can have one mutable reference. And so this is including the owning var itself. So includes owner. And I guess so we can have read-only references, or we can have mutable references. So that's write reference. But what about moving? Are these things allowed to move? And no, they're not allowed to move. So borrows cannot perform moves. Only the owning variable can move ownership. So that has nothing to do with borrows, or at least, sorry, I mean, of course they end up being related, but a borrow can't perform a move. Okay. I mentioned that the permissions to the owner get reduced. So they don't get reduced permanently. They get reduced temporarily. But okay, what is the duration? So while these references are alive or active, maybe, the read and write permissions and move perms are reduced for the owner. So the owner has reduced permissions while these borrows are alive, and I'll explain what that means in a second. Whoops, I meant a different button. Okay, I like to represent things like this in a table, so let's do that. So we'll make V on the left-hand side. So we're going to think about a mutable V. We're going to think about a shared reference to V. And we're going to think about a writable reference to V. So these are the three cases. And what I would like to do is write out, I think I'm going to need some space. I would like to write out for what if there are no borrows active? What if there are shared borrows active? I'll just call that borrow. And what if there is mute borrows active? So mute borrow. Okay, need even more space. Now, what I want to think about, or what I want to illustrate is what are the permissions like in these cases? Well, in the case that we have, so maybe this top row could be a little more informative if I made a note explaining what it is. So this is what borrows are alive. So the owner is alive, but this column here, this is going to be the case that there's no borrows, just the owner alive. So in that case, well, for a mutable V, we have read permissions, we have write permissions, and we have move permissions. We're allowed to do all of those. Whoops. Wonderful. In the case that there's no borrow, neither of these exist. So this case, it doesn't have them. So we can just cancel those cells out here. Okay, what about in the case that there is a borrow alive? So maybe we'll start with the borrow. Okay, so this is a shared borrow, which is in the case of, with aliasing XOR mutability, multiple read-only references. A shared borrow is a read-only reference. So we have read permissions, of course, read-only. Read-only means we do not have write permissions. And it means so borrows can't move. That's another thing I said. We can't move. So no moving. And I'm going to need to make my table line up a bit better. Nice. Okay, so while this exists, since we can only have one, so we're XOR with a mutable reference. So what that means is the owner has their permissions reduced. So we can read from the owner, but we can't write. And while the borrow is active, we can't move. So this is the way that a shared borrow being alive changes the permissions of the owning variable. So write permissions are gone and move permissions are gone until this is inactive, not alive. While we have a shared borrow alive like this, we are not allowed to create a mutable borrow because that would end up in the situation where we have read-only references and we have mutable references. So we're not allowed to create one of them. Okay, what about in the case where we have a mutable borrow that's alive? We'll start with the mutable borrow. Well, in that case, we can read it. We can also write it, but it's a borrow, so we're not allowed to move. Oops, M. And if we're allowed to write, well, then for our original variable, we're in this situation. This mute v is the mutable reference, and so we remove read permissions. We're not allowed to read, otherwise we'd have both sides of this. We're not allowed to write, and we're not allowed to move while that mutable borrow is active. So all permissions get taken away from the owning variable while the mutable borrow is out and about. Okay, that looks neater. Now, while there is this writable reference in existence, we're not allowed to create a shared borrow. That is banned by this rule, aliasing XOR mutability. Okay, so this is the set of permissions that happen at any point in time while borrows are alive. Maybe the next thing to point out is, when are borrowers alive and not? When are borrowers alive? That's the good question. And they start obviously when they get brought in. So from what would you call that? From instantiation? I don't know. An instantiation until last usage. So after the last usage, the mutability permissions get restored because these borrows stop existing. That's the lifetime. We call that the lifetime. It's the lifetime. Okay, cool. So let's write some more. Let's write better versions of these actually that are going to showcase these permissions. So as I mentioned, these suck. Whoa, did I not grab that? These suck. We want a better way to do this. So let's call this, we're going to do, instead of do reads, we're going to borrow. Instead of do writes, we're going to mute borrow. And we're going to use references instead. So, did I? Oh no, I changed the capitalization on this. Ooh, let me peel back quickly. Okay, that looks better. All right, trust the process, everyone. Okay. Oops, borrow I think is better because the function up above there is called borrowing. So this one can just be called borrow. Whoops, I nearly did exactly that. So arg, now we want to take a reference, and because we're taking a shared reference, because we're going to do some reads in here, we aren't going to return anything. So we don't need to return the arg anymore. And we can say we're in borrow. Yep, that looks like it would make sense. And here, we don't need a mutable arg. What we need is a mutable reference. And because of that, we don't need to have a return value here anymore. Get rid of arg at the end here. We can push 3. Maybe we'll push 4 because we're pushing 3 down the bottom here. Cool. And so these aren't being called. Let's do one by one. So I'm going to get rid of that for the moment. Okay, so after we've done these reads and writes, let's call borrow. So borrow is going to need to be provided with a shared reference to V. So let's make one. Let's go let shared V equal to a shared reference to V. So as I mentioned up here, this is like the instantiation. So what do I want to say here? This is alive at this point. And when it becomes alive, what we know about the owner is owner is now read only and cannot move. And so we can provide this to borrow. So this is all type checks, it's legal. And what else do we know? We know that this is the last usage, like literally the last usage. So, whoops, for some reason that didn't look right. Is something? Okay, whatever. So here, share V is dead, and owner has write permissions and move perms restored. Okay, so what we should see then is in the middle here, in this area here, this is inside the lifetime of this shared borrow. And so if we do something like print line, in fact, I might steal a print line. That will be faster. Print line during shared V. And we'll do that for V. So this is read. Read. Is that all good? Well, it's type checking. And if I run it, maybe I'll do a do write. This is after. And I'll put a new line. Whoop, there we go. Okay, but we're in share V, so we can do a read. We're in the middle of it and we're actively reading, so that's okay. Whoops. That's okay. What if we wanted to do, and then inside the borrow, this is performing a read as well, we see. Whoops. So, okay, we're allowed to do the read. Now, our permissions table here says that we shouldn't be allowed to do a write and we shouldn't be allowed to do a move. So let's try and do a write. So v dot push 4032 even. It's all good. And no, we're not allowed to do that. It says you cannot borrow v as mutable because it is borrow's immutable. Okay, well, sorry, we're not creating mutable borrow there. Maybe what I should do instead is I should try and do v0 equals 32. Try to mutate v. Well, give me a better error message then. This is still a borrow. Okay, well, either way, the point that I'm getting across is mutability is not allowed. So mute or write, not okay. And if we try to do a drop of v, which is a move of v into the argument, we cannot move out of v because it is borrowed. And so that is not allowed either. So move, not okay. And so that matches up that we were allowed to read while we had the shared borrow active. We were not allowed to write, and we were not allowed to move and using v. So while share v was alive, v had reduced permissions. Okay, but after here, we I'm just going to take this and we're going to do the same thing again, but we're going to do it with mute borrow. So mute borrow does not want a shared v, it wants a MBV, which means mute borrow v. So we have to change this to be a mutable borrow. MBV is alive at this point. The owner is now neither read nor write. So we can't do either. That's what our table told us. While this mute v was active, we're neither read, neither write, and we cannot move. So that's the situation that we're in. During MBV, I'm just going to fix off a bit of this. So MBV is dead. Owner has read and write permissions and move perms restored. Fantastic. Okay, so let's check. Here, are we allowed to do this read? We are not. It cannot be borrowed as immutable. So that's a shared reference, a read-only reference, because it is borrowed as immutable, and it tells us where the immutable one is. So this is not okay. So that failed. What about a write? If we try to do a write, it has mutable permissions. But because we have a mutable borrow, we can't do a mutable borrow more than once at a time. So the second mutable borrow is here, which is happening because of this assignment. So write is also not okay, and drop will also be not okay. We cannot move out of v because it is borrowed. The borrow occurs up here. So that is also not okay, which matches up with our expectations. While we have read and write permissions, all of these are reduced for v. And so we were trying these on v. Okay, but afterwards they get restored. So let's have let's do these things again, I guess. At end, let's go. Well, we want to be able to witness the fact that we changed the front to 32. So 32 change. Okay. So this type checked, and if I run it, what do we see? Indeed, it worked. So at the end, permissions got restored. We were able to do our read here. We got 1, 2, 3, 4, which implies that in MB, we did add our 4 on there. And then we changed the first position to 32. And we saw that after 32 change, that got changed. So after the mute borrow, which was restricting the access on V, we were able to do a read, a write, and we moved. So all of these became okay. And that corresponds to going back to this position. So aliasing XOR mutability is useful. We get to allow there to be safe control over what permissions are happening at one time. We want to be in the situation where there's only one reader of data, and that way we can't get into data race scenarios. And it's fine to have, if there's no one that has write permissions, then it's fine to have read permissions across multiple things, because no one's going to go and change that data. So there's no risk of like a data race or anything like that happening. That's all that I have to cover. And yep, if I look at my notes, I think I touched on every one of those points. So thank you for allowing me the opportunity to talk about this stuff and write out some examples. I hope it was instructive for everyone, and I look forward to, I guess, the next opportunity to share something. Thank you.